Francium. Francium is a chemical element with symbol Fr and atomic number 87. It used to be known as eka-caesium. It is extremely radioactive. Its most stable isotope, Francium-223, has a half-life of only 22 minutes. It is the second most electropositive element, behind only cesium, and is the second rarest naturally occurring element. The isotopes of francium decay quickly into astatine, radium, and radon. The electronic structure of a francium atom is 7s1, and so the element is classed as an alkali metal. Bulk francium has never been viewed. Because of the general appearance of the other elements in its periodic table column, it is assumed that francium would appear as a highly reactive metal, if enough could be collected together to be viewed as a bulk solid or liquid. Obtaining such a sample is highly improbable, since the extreme heat of decay caused by its short half-life would immediately vaporize any viewable quantity of the element. Francium was discovered by Marguerite Curie in France in 1939. It was the last element first discovered in nature, rather than by synthesis. Outside the laboratory, francium is extremely rare, with trace amounts found in uranium and thorium ores, where the isotope Francium-223 continually forms and decays. As little as 20-30 G exists at any given time throughout the Earth's crust. The other isotopes are entirely synthetic. The largest amount produced in the laboratory was a cluster of more than 300,000 atoms. Francium is one of the most unstable of the naturally occurring elements. Its longest-lived isotope, Francium-223, has a half-life of only 22 minutes. The only comparable element is astatine, whose most stable natural isotope, astatine-219, has a half-life of 56 seconds, although synthetic astatine-210 is much longer lived with a half-life of 8.1 hours. All isotopes of francium decay into astatine, radium, or radon. Francium-223 also has a shorter half-life than the longest-lived isotope of each synthetic element up to and including element 105, dubnium. Francium is an alkali metal whose chemical properties mostly resemble those of cesium. A heavy element with a single valence electron, it has the highest equivalent weight of any element. Liquid francium, if created, should have a surface tension of 0.05092 N/m at its melting point. Francium's melting point was calculated to be around 27 degrees C. The melting point is uncertain because of the element's extreme rarity and radioactivity. The estimated boiling point of 677 degrees C is also uncertain. Linus Pauling estimated the electronegativity of francium at 0.7 on the Pauling scale, the same as cesium. The value for cesium has since been refined to 0.79, but there are no experimental data to allow refinement of the value for francium. Francium has a slightly higher ionization energy than cesium, 392.811 kJ/mol as opposed to 375.7041 kJ/mol for cesium, as would be expected from relativistic effects, and this would imply that cesium is the less electronegative of the two. Francium should also have a higher electron affinity than cesium, and the Fr ion should be more polarizable than the Cs ion. The CsFr molecule is predicted to have francium at the negative end of the dipole, unlike all known heterodiatomic alkali metal molecules. Francium superoxide is expected to have a more covalent character than its lighter congeners. This is attributed to the 6p electrons in francium being more involved in the francium-oxygen bonding. Francium coprecipitates with several cesium salts, such as cesium perchlorate, which results in small amounts of francium perchlorate. This coprecipitation can be used to isolate francium, by adapting the radiocesium coprecipitation method of Lawrence E. Glendinning and Nelson. It will additionally coprecipitate with many other cesium salts, including the iodate, the picrate, the tartrate, the chloroplatinate, and the silicotungstate. It also coprecipitates with silicotungstic acid, and with perchloric acid, without another alkali metal as a carrier, which provides other methods of separation. Nearly all francium salts are water-soluble. There are 34 known isotopes of francium ranging in atomic mass from 199 to 232. Francium has 7 metastable nuclear isomers. Francium 223 and Francium 221 are the only isotopes that occur in nature, though the former is far more common. Francium 223 is the most stable isotope, with a half-life of 21.8 minutes, and it is highly unlikely that an isotope of francium with a longer half-life will ever be discovered or synthesized. Francium 223 is the fifth product of the actinium decay series as the daughter isotope of actinium 227. Francium 223 then decays into radium 223 by beta decay, with a minor alpha decay path to astatine 219. Francium 221 has a half-life of 4.8 minutes. It is the ninth product of the neptunium decay series as a daughter isotope of actinium 225. Francium 221 then decays into astatine 217 by alpha decay. The least stable ground state isotope is francium 215, with a half-life of 0.12 ms. It undergoes a 9.54 MeV alpha decay to astatine 211. Its metastable isomer, francium 215M, is less stable still, with a half-life of only 3.5 ns. Due to its instability and rarity, there are no commercial applications for francium. It has been used for research purposes in the fields of chemistry and of atomic structure. Its use as a potential diagnostic aid for various cancers has also been explored, but this application has been deemed impractical. Francium's ability to be synthesized, trapped, and cooled, along with its relatively simple atomic structure, has made it the subject of specialized spectroscopy experiments. These experiments have led to more specific information regarding energy levels and the coupling constants between subatomic particles. Studies on the light emitted by laser-trapped francium-210 ions have provided accurate data on transitions between atomic energy levels which are fairly similar to those predicted by quantum theory. As early as 1870, chemists thought that there should be an alkali metal beyond cesium, with an atomic number of 87. It was then referred to by the provisional name eka-caesium. Research teams attempted to locate and isolate this missing element, and at least 4 false claims were made that the element had been found before an authentic discovery was made. Soviet chemist D.K. Dobrozherdov was the first scientist to claim to have found eka-caesium, or francium. In 1925, he observed weak radioactivity in a sample of potassium, another alkali metal, and incorrectly concluded that eka-caesium was contaminating the sample. He then published a thesis on his predictions of the properties of eka-caesium, in which he named the element russium after his home country. Shortly thereafter, Dobrozherdov began to focus on his teaching career at the Polytechnic Institute of Odessa, and he did not pursue the element further. The following year, English chemists Gerald J. F. Druce and Frederick H. Loring analyzed X-ray photographs of manganese sulfate. They observed spectral lines which they presumed to be of eka-caesium. They announced their discovery of element 87 and proposed the name alkalinium, as it would be the heaviest alkali metal. In 1930, Fred Allison of the Alabama Polytechnic Institute claimed to have discovered element 87 when analyzing pollucite and lepidolite using his magneto-optical machine. Allison requested that it be named Virginium after his home state of Virginia, along with the symbols 6 and Vm. In 1934, H. G. Macpherson of UC Berkeley disproved the effectiveness of Allison's device and the validity of his discovery. In 1936, Romanian physicist Horia Hulabii and his French colleague Yvette Cauchoy also analyzed pollucite, this time using their high-resolution X-ray apparatus. They observed several weak emission lines, which they presumed to be those of element 87. Hulabii and Cauchoy reported their discovery and proposed the name Moldavium, along with the symbol ML, after Moldavia, the Romanian province where Hulabii was born. In 1937, Hulabii's work was criticized by American physicist F. H. Hirsch Jr., who rejected Hulabii's research methods. Hirsch was certain that eka-caesium would not be found in nature, and that Hulabii had instead observed mercury or bismuth X-ray lines. Hulabii insisted that his X-ray apparatus and methods were too accurate to make such a mistake. Because of this, Jean-Baptiste Perrin, Nobel Prize winner and Hulabii's mentor, endorsed moldavium as the true eka-caesium over Marguerite Curie's recently discovered francium. Curie took pains to be accurate and detailed in her criticism of Hulabi's work, and finally she was credited as the sole discoverer of element 87. All other previous purported discoveries of element 87 were ruled out due to francium's very limited half-life. Eka-caesium was discovered on January 7, 1939 by Marguerite Curie of the Curie Institute in Paris, when she purified a sample of actinium-227 which had been reported to have a decay energy of 220 keV. Curie noticed decay particles with an energy level below 80 keV. Curie thought this decay activity might have been caused by a previously unidentified decay product, one which was separated during purification, but emerged again out of the pure actinium-227. Various tests eliminated the possibility of the unknown element being thorium, radium, lead, bismuth, or thallium. The new product exhibited chemical properties of an alkali metal, which led Curie to believe that it was element 87, produced by the alpha decay of actinium-227. Curie then attempted to determine the proportion of beta decay to alpha decay in actinium-227. Her first test put the alpha branching at 0.6%, a figure which she later revised to 1%. Curie named the new isotope actinium K, and in 1946, she proposed the name caesium for her newly discovered element, as she believed it to be the most electropositive cation of the elements. Irene Joliot-Curie, one of Curie's supervisors, opposed the name due to its connotation of cat rather than cation. Furthermore, the symbol coincided with that which had since been assigned to curium. Curie then suggested francium, after France. This name was officially adopted by the International Union of Pure and Applied Chemistry in 1949, becoming the second element after gallium to be named after France. It was assigned the symbol Fa, but this abbreviation was revised to the current FR shortly thereafter. Francium was the last element discovered in nature, rather than synthesized, following hafnium and rhenium. Further research into francium's structure was carried out by, among others, Sylvain Lieberman and his team at CERN in the 1970s and 1980s. 223Fr is the result of the alpha decay of 227Ac and can be found in trace amounts in uranium minerals. In a given sample of uranium, there is estimated to be only one francium atom for every 1 × 1018 uranium atoms. It is also calculated that there is at most 30 G of francium in the Earth's crust at any given time. Francium can be synthesized by a fusion reaction when a gold-197 target is bombarded with a beam of oxygen-18 atoms from a linear accelerator in a process originally developed in the physics department at the State University of New York at Stony Brook in 1995. Depending on the energy of the oxygen beam, the reaction can yield francium isotopes with masses of 209, 210, and 211. The francium atoms leave the gold target as ions, which are neutralized by collision with yttrium and then isolated in a magneto-optical trap in a gaseous unconsolidated state. Although the atoms only remain in the trap for about 30 seconds before escaping or undergoing nuclear decay, the process supplies a continual stream of fresh atoms. The result is a steady state containing a fairly constant number of atoms for a much longer time. The original apparatus could trap up to a few thousand atoms, while a later improved design could trap over 300,000 at a time. Sensitive measurements of the light emitted and absorbed by the trapped atoms provided the first experimental results on various transitions between atomic energy levels in francium. Initial measurements show very good agreement between experimental values and calculations based on quantum theory. The research project using this production method relocated to Triumph in 2012, where over 106 francium atoms have been held at a time, including large amounts of 209Fr in addition to 207Fr and 221Fr. Other synthesis methods include bombarding radium with neutrons, and bombarding thorium with protons, deuterons, or helium ions. 223Fr can also be isolated from samples of its parent 227Ac, the francium being milked via elution with NH4Cl-CrO3 from an actinium-containing cation exchanger and purified by passing the solution through a silicon dioxide compound loaded with barium sulfate. In 1996, the Stony Brook group trapped 3,000 atoms in their MOT, which was enough for a video camera to capture the light given off by the atoms as they fluoresce. Francium has not been synthesized in amounts large enough to weigh.